Okay. Looking a little more closely at the picture we had before and bringing it down to its most basic essence. We have vector space V, vector space W, transformation defined by a matrix. In the example we're talking about, V is R3, W is R5. Now we could have more data. We could have 12 data points, so the W would be R12, okay? But V is R3 because we're doing a quadratic model and we're looking for A, B, and C. We're looking for the vector X equal to A, B, C such that T of X, transform vector of X, which is A times X, is as close as possible to a vector B that represents the Y values that we observed in our depth versus time graph. So our vector B is over here somewhere. That last time I drew it in the first quadrant, so I'm going to draw one here in the third quadrant just to show that it's not always the same. And the directions of C and N, they can be rotated any way. They could still represent. There's nothing special about the way I've got this rotated, but I don't want to do it horizontal and vertical because that's a special set of directions. And you don't know for given set of data what matrix A you're going to get, so you don't know how these spaces are going to be oriented within R5. And they're not going to be lines anyway. C is going to be not really a line. Actually, a three-dimensional subspace of W. But I'm representing it by a line because that's the simplest representation that gets across the idea that we want to have. And N is your null space of A transpose. And maybe I better write it as null space of A transpose. Right now, we don't have to worry about that. That's an easy null space to find, as is the column space, just by matrix reduction and so forth. And also in the column space is the row space of A transpose. And I wrote that before. I'm just going to call it the column space of the matrix A. And it consists of all the vectors that you get from by transforming vector V according to this transformation, by multiplying vectors in V, vectors in R3, by, excuse me, by the matrix A. Okay. Now, the AX over here that's as close as possible to B, well, AX has to be in C. Okay, AX is a vector in C. Because of why? X is a vector over here. And C consists of all the images of vectors in X in the space W. Okay, well, what vector is closest to B? What vector in C is closest to B? Well, according to this picture, it should be the projection parallel to the null space. Recall also that these two spaces, this being the row space of A transpose, this being the null space of A transpose, these two have to be orthogonal. So this is an orthogonal projection. You take an orthogonal projection of B onto C, and you find this vector, and this vector is your AX. That is represented, you know, I'm being a little ambiguous using an arrow and a point, but so be it, okay? This point represents AX in the blobby space, but this arrow is another way of looking at it if we regard this as our column space of A. So that AX is equal to B added to some vector in N of A transpose. So that, okay, here's B, here's some vector in the null space of A transpose. And I hope you understand that by being parallel to this axis makes that vector a member of N of A transpose, an element in A transpose. Okay, so that again we get the idea that, as we stated before, AX minus B and AX minus B with the arrows would be this, plus a vector in this direction, which would be back here. It would be this, and that would be this vector here. Okay, AX minus B is in the null space of A transpose, and I'm just repeating what we said before. So A transpose of AX minus B is 0. And I'll write one more step. So A transpose AX equals A transpose B. Now I've skipped a step of the algebra, but it's, A transpose AX minus A transpose B equals the 0 vector. So A transpose AX equals what you get when you add A transpose B to both sides, which is just A transpose B over here. Okay? And this is a solvable system. This is how we find the X over here. So by solving this system, we find the X that maps to this vector. Here's our X equals ABC so our model is y equals AT squared plus BT plus C.